Saturn shouldn't exist. This giant planet, with its stunning rings and impossible lightness, breaks the rules of how worlds are supposed to form. It's less dense than water, meaning it would actually float if you could find an ocean big enough. And those rings, those beautiful, bright bands of ice circling the planet, they're far too young and perfect to make sense in a solar system that's been around for 4.5 billion years. Everything about Saturn screams impossibility, and yet there it is, the jewel of our cosmic neighborhood. So how did this happen? How did nature create something that seems to violate its own laws? The answer takes us on a journey through shattered moons, migrating giants, and a solar system far more violent than anyone imagined. Let's start with the most obvious mystery. Saturn is enormous, the second largest planet in our solar system, nearly 10 times wider than Earth. You could fit over 700 Earths inside Saturn's volume. But here's the catch. Despite all that size, Saturn is remarkably light. When scientists measure its density, they find something shocking. Saturn has a density of just 0.69 grams per cubic centimeter. Water, for comparison, has a density of 1 gram per cubic centimeter. That means Saturn is actually less dense than the water in your kitchen sink. If you could somehow place Saturn in a cosmic bathtub, it would bob on the surface like a beach ball. This is not how planets are supposed to work. Think about it this way. Planets form from the collapse of gas and dust in space. Gravity pulls material together, compressing it, making it denser. The bigger the planet, the stronger the gravity, and the more compressed everything becomes. Jupiter, Saturn's larger neighbor, is also a gas giant, but it's significantly denser. Earth is even denser because it's made of rock and metal. But Saturn seems to have missed the memo. It's as if someone inflated a balloon the size of a world and filled it with the lightest possible materials. How does a planet get so big yet remain so impossibly light? The answer lies in Saturn's composition. Saturn is made almost entirely of hydrogen and helium, the two lightest elements in the universe. These are the same materials that make up the Sun and most other stars. In fact, Saturn's chemical makeup is remarkably similar to the Sun's. About 96% of Saturn is hydrogen, and most of the rest is helium. There are trace amounts of other materials, methane, ammonia, water vapor, but they're just tiny fractions of the total. So Saturn is essentially a ball of the universe's lightest gases, compressed by gravity into a planet-sized sphere. But even that doesn't fully explain the density problem. After all, Jupiter is also made of hydrogen and helium, and it's denser. The difference comes down to pressure and temperature. Deep inside Jupiter, the pressure is so intense that hydrogen behaves in strange ways. It gets squeezed so hard that it stops being a gas and becomes a liquid. Go even deeper, and the pressure becomes so extreme that hydrogen transforms into something called liquid metallic hydrogen, a bizarre state of matter where hydrogen acts like a liquid metal, conducting electricity. This liquid metallic hydrogen is incredibly dense, and Jupiter has a lot of it. That's part of why Jupiter is denser overall. To really understand this, we need to think about what pressure actually means at these scales. When we talk about pressure on Earth, we're usually talking about atmospheric pressure, the weight of all the air above us pushing down. At sea level, that's about 15 pounds per square inch. That might not sound like much, but it's enough to keep water liquid and to keep our bodies functioning. Now imagine going deeper. If you dive underwater, the pressure increases. For every 10 meters you descend, the pressure increases by about 1 atmosphere. At the bottom of the deepest ocean trenches, about 11 kilometers down, the pressure is over 1,000 times atmospheric pressure. That's enough to crush most submarines like tin cans. But even that incredible pressure is nothing compared to what exists inside a gas giant. At the center of Saturn, the pressure is estimated to be around 8 million times Earth's atmospheric pressure. That's 8 million times the pressure you feel standing at sea level. At those pressures, matter behaves in ways that are completely alien to our everyday experience. Atoms get pushed so close together that the normal rules of chemistry break down. Electrons can't stay in their usual orbits around atomic nuclei. Instead, they get squeezed out and start moving freely through the material, creating a sea of electrons that can conduct electricity just like the electrons in a copper wire. This is what happens to hydrogen deep inside Saturn. Under normal conditions, hydrogen exists as H2 molecules, two hydrogen atoms bonded together. Each molecule is electrically neutral, and hydrogen gas doesn't conduct electricity. But when you compress hydrogen to millions of atmospheres of pressure, the molecules break apart. The hydrogen atoms get packed so tightly that their electrons are shared between many atoms, creating a metallic bond. The result is a substance that looks and acts like a liquid metal, even though it's made of the lightest element in the universe. Scientists have been trying to create liquid metallic hydrogen in laboratories for decades. It's incredibly difficult because you need to recreate the extreme pressures found inside giant planets. Some experiments have used diamond anvil cells, devices that squeeze tiny samples between two diamonds to create enormous pressures. Others have used powerful lasers or high-speed impacts to briefly achieve the conditions necessary for metallic hydrogen. In 2016, researchers at Harvard claimed to have created solid metallic hydrogen for the first time, although the sample disappeared before it could be thoroughly studied. These experiments are important because they help us understand what's happening inside planets like Saturn and Jupiter, worlds where these extreme conditions exist naturally. The presence of liquid metallic hydrogen inside Saturn has profound effects on the planet's properties. For one thing, it determines the planet's magnetic field. As Saturn rotates, the liquid metallic hydrogen in its interior swirls and flows, driven by convection and the planet's rotation. This flowing, electrically conducting fluid acts like a giant dynamo, converting mechanical energy into magnetic energy. The result is a planetary magnetic field that extends far into space, creating a magnetosphere that protects Saturn from the solar wind and traps charged particles from the sun. Saturn's magnetosphere is about 1 million kilometers across, large enough to contain the entire planet and its rings and many of its moons. Within this magnetosphere, charged particles spiral along magnetic field lines, creating radiation belts similar to Earth's Van Allen belts. These particles can be dangerous to spacecraft. When the Cassini probe was studying Saturn, it had to carefully navigate through the magnetosphere to avoid regions of intense radiation that could damage its electronics. The magnetosphere also interacts with Saturn's moons, particularly Enceladus, which releases water vapor and ice particles into space. These particles become ionized and get trapped in Saturn's magnetic field, creating a torus of plasma that extends along Enceladus's orbit. But there's more to Saturn's interior than just liquid metallic hydrogen. At the very center of the planet, there's a core made of heavier elements, rock and ice compressed to incredible densities. This core is where Saturn began its life as a seed of solid material that grew by accumulating more and more material from the surrounding protoplanetary disk. Scientists estimate that Saturn's core is probably 10 to 20 times the mass of Earth, although there's still uncertainty about its exact size and composition. The core is important because it's what allowed Saturn to capture all that hydrogen and helium in the first place. When Saturn was forming, it started as a relatively small object, maybe 10 to 15 Earth masses. At this size, it had enough gravity to hold onto ice and rock, but not enough to capture significant amounts of hydrogen and helium gas. These light gases were abundant in the protoplanetary disk, but they moved too fast to be captured by the gravity of a small object. But as Saturn's core grew, its gravity became stronger, and eventually it reached a critical mass, somewhere around 15 Earth masses, where it could start capturing hydrogen and helium. Once this threshold was crossed, Saturn's growth accelerated dramatically. Hydrogen and helium from the surrounding disk began falling onto the planet in a runaway process. The more gas Saturn captured, the stronger its gravity became, and the more gas it could capture. This process continued until either Saturn had captured all the available gas in its vicinity, or until something disrupted the disk and shut off the supply of gas. The result was a planet with a small, dense core surrounded by a massive envelope of hydrogen and helium, a structure that's common to all gas giants. But the exact structure of Saturn's interior is still somewhat mysterious. We can't see inside the planet directly, so we have to infer its structure from indirect measurements. Scientists use data about Saturn's gravitational field measured by tracking the orbits of spacecraft and moons around the planet. These measurements tell us how mass is distributed inside Saturn, which gives us clues about the size of the core and the transitions between different layers. They also use data about Saturn's rotation, its shape, and its magnetic field to build computer models of the interior. These models are tested and refined as new data becomes available, but there's still a lot of uncertainty, particularly about the boundary between the liquid hydrogen layer and the liquid metallic hydrogen layer. Saturn also has liquid metallic hydrogen in its core, but not as much of it. Saturn's internal pressure isn't quite as extreme as Jupiter's because Saturn is smaller and has less mass. Less mass means less gravitational compression, which means less pressure deep inside. So Saturn has a smaller core of liquid metallic hydrogen surrounded by a thicker layer of ordinary liquid hydrogen, and then a massive atmosphere of gaseous hydrogen and helium. All those lighter layers bring down Saturn's average density. It's like the difference between a tightly packed snowball and a fluffy pile of snow. Same material, different densities. But there's another piece to this puzzle. Saturn is also hot. Not hot like the Sun, but hot compared to what you'd expect for a planet so far from the Sun. Saturn orbits nearly 10 times farther from the Sun than Earth does. At that distance, sunlight is weak and cold. The temperature at the top of Saturn's clouds is around minus 140 degrees Celsius, which is brutally cold. But here's the weird part. Saturn radiates more heat into space than it receives from the Sun. It's actually generating its own internal heat, like a slow burning furnace deep inside the planet. Where does this extra heat come from? It's not from nuclear fusion like in the Sun. Saturn isn't massive enough to ignite fusion reactions in its core. Instead, the heat comes from a process called gravitational contraction. Essentially, Saturn is still slowly shrinking. The planet's gravity is pulling all that hydrogen and helium inward, compressing it bit by bit. As the material gets compressed, it heats up, just like when you squeeze air in a bicycle pump and the pump gets warm. This slow, gradual collapse releases energy, and that energy radiates out as heat. Saturn has been doing this for billions of years, slowly contracting and slowly releasing heat. But even this creates a problem. According to our models of planetary formation and evolution, Saturn should have cooled down and stopped radiating so much excess heat by now. The planet is 4.5 billion years old, the same age as the solar system itself. By this point, most of that initial heat from formation should have dissipated into space. Saturn should be a cold, quiet world, slowly cooling like an ember fading in the darkness. Instead, it's still warm, still active, still radiating heat as if it's much younger than it should be. It's another piece of the Saturn paradox. And then there are the rings. Oh, those glorious rings. They're the first thing anyone notices about Saturn, the feature that makes it instantly recognizable even to people who know nothing about astronomy. The rings are vast, stretching hundreds of thousands of kilometers from the planet, yet they're incredibly thin, in some places only tens of meters thick. Imagine a disk of ice and rock that's wider than the distance from Earth to the Moon, but thin enough that if you scaled it down to the size of a football field, it would be thinner than a sheet of paper. That's Saturn's rings. The discovery of Saturn's rings is one of the great stories in the history of astronomy. When Galileo Galilei first turned his telescope towards Saturn in 1610, he saw something strange. His telescope wasn't powerful enough to resolve the rings clearly, so what he saw looked like three bodies. Saturn itself with two smaller objects on either side. He wrote that Saturn appeared to have ears or handles. Over the next few years, Galileo continued to observe Saturn, and he noticed something puzzling. Sometimes the ears were visible, and sometimes they seemed to disappear. This confused him greatly, and he never figured out what he was looking at. It wasn't until 1655 that Dutch astronomer Christian Huygens, using a more powerful telescope, realized that Saturn was surrounded by a thin, flat ring that didn't touch the planet. Even Huygens' discovery didn't settle the matter, though. Other astronomers observed Saturn and saw different things. Some saw a single ring, others saw multiple rings, and there was considerable debate about whether the rings were solid or made of separate pieces. It took another 100 years before the French astronomer Jean-Baptiste Cassini, in 1675, discovered a dark gap in the rings, now called the Cassini division. This gap suggested that the rings were not a single solid disk, but had structure and divisions. Later observations revealed even more divisions and gaps, and by the 19th century, astronomers had figured out that the rings couldn't be solid at all. If they were solid, tidal forces from Saturn would tear them apart. The physicist James Clerk Maxwell proved mathematically in 1859 that Saturn's rings had to be made of countless small particles, each one orbiting Saturn independently. This was a revolutionary idea at the time, and it explained many of the ring's observed properties. The particles in the inner parts of the rings orbit faster than those in the outer parts, just as planets closer to the Sun orbit faster than those farther out. This difference in orbital speeds creates shear forces that would rip apart any solid structure, but individual particles can orbit at their own speeds without problem. Maxwell's work laid the foundation for our modern understanding of planetary rings. We now know that Saturn's rings are indeed made of countless individual particles, ranging in size from tiny grains of dust smaller than a grain of sand to house-sized boulders. Most of the ring particles are somewhere in between, roughly the size of snowballs or basketballs. Each particle is essentially a little moon, orbiting Saturn according to the laws of gravity and orbital mechanics. The particles are packed closely enough that they collide with each other frequently, billions of collisions happening every second across the entire ring system. These collisions are generally gentle, with particles bouncing off each other or sticking together temporarily before breaking apart again. The rings are also incredibly flat. If you were to look at them edge-on, they would appear as a thin line, barely visible even though they stretch for hundreds of thousands of kilometers. This flatness is a result of collisions between particles. Imagine a particle orbiting Saturn in an inclined orbit, tilted relative to Saturn's equator. Every time this particle passes through the main ring plane, it collides with other particles. These collisions gradually change its orbit, flattening it out until it's orbiting in the same plane as everything else. Over time, all the particles end up orbiting in a thin disk aligned with Saturn's equator, like a giant spinning pizza. The rings are divided into several major sections, each with its own characteristics. The main rings, the ones visible from Earth with even a small telescope, are labeled A, B, and C. The B ring is the brightest and most massive, containing the bulk of the ring material. It's incredibly dense, with particles packed so closely together that in some regions you can't see through the ring at all. The A ring is also bright but less dense than the B ring. It's separated from the B ring by the Cassini division, that dark gap discovered in 1675. The Cassini division is about 5,000 kilometers wide, and it's not completely empty. There are still ring particles there, but they're much more sparse, creating a dark band in contrast to the bright rings on either side. The C ring is fainter and more translucent than the A and B rings. It's sometimes called the crepe ring because of its gauzy appearance. The C ring extends from the inner edge of the B ring down towards Saturn's cloud tops, and it contains much less material than the brighter rings. Beyond the main rings, there are several fainter rings that were only discovered with spacecraft and sensitive telescopes. The D ring lies inside the C ring, very close to Saturn's atmosphere. The F ring lies just outside the A ring, and it's a narrow, braided ring with a complex structure maintained by two small shepherd moons. The G and E rings are extremely faint and diffuse, made mostly of tiny dust particles rather than the larger ice chunks found in the main rings. Each of these rings has its own story. The E ring, for example, is fed by geysers on Enceladus, a small icy moon that orbits within the ring. These geysers shoot water vapor and ice, particles into space, and some of this material goes into orbit around Saturn, creating a diffuse torus of particles that extends along Enceladus's entire orbital path. The F ring is shaped by the gravitational influence of two small moons called Prometheus and Pandora, which orbit on either side of the ring. These shepherd moons keep the ring particles confined to a narrow band, and their gravitational tugs create waves and kinks in the ring that change over time. But the real mystery isn't just the structure of the rings, it's their age and composition. The rings are made almost entirely of water ice, as pure as the ice in your freezer, with only tiny amounts of rocky material mixed in. This purity is visible in the ring's color. They're not gray or brown like you might expect for ancient space debris. They're brilliantly white, reflecting nearly as much sunlight as fresh snow. When the Cassini spacecraft analyzed the composition of the rings using spectroscopy, breaking down the reflected light into its component wavelengths, it confirmed that the rings are at least 99% pure water ice. This purity is shocking because space is a dirty place. Interplanetary space is filled with dust, tiny particles of rock and carbon that come from asteroids, comets, and even from outside the solar system. This dust is constantly falling into the Saturn system, and some of it lands on the rings. Over time, you'd expect this contamination to darken the rings, turning them from bright white to dull gray or brown. The rate of contamination depends on how much dust is in the area and how long the rings have been exposed, but based on measurements from Cassini and other spacecraft, scientists can estimate how dirty the rings should be for a given age. And here's where things get interesting. When scientists calculated how much contamination the rings should have accumulated over the age of the solar system, 4.5 billion years, they found that the rings should be much, much darker than they actually are. In fact, if the rings were that old, they should be almost black, completely covered in a thick layer of space dust. The fact that they're still bright and clean suggests that they're much younger, perhaps only a few 100 million years old, or even just tens of millions of years old. That's incredibly young on a cosmic timescale. To put it in perspective, if the solar system's history were compressed into a single year, the rings would have formed sometime in the last few days or weeks. The rings are also stunningly beautiful. They shine brilliantly in sunlight, reflecting more light than the planet itself. When you look at Saturn through a telescope, the rings are often brighter than the cloud tops, gleaming like polished silver against the darkness of space. They're divided into distinct bands, separated by gaps and divisions, each ring traveling at its own speed in a carefully choreographed cosmic dance. The whole system is elegant, precise, and utterly mesmerizing. But here's the problem. The rings shouldn't be there, or at least they shouldn't look the way they do. Based on everything we know about planetary science, Saturn's rings should have disappeared long ago, or at least degraded into a dark, dirty mess. Instead, they're pristine, bright, and apparently young. How young? Recent studies suggest the rings might be only 10 million to 100 million years old. That's incredibly young in cosmic terms. The solar system is 4.5 billion years old. The rings are less than 2% of that age. In geological terms, it's like finding a brand new building in the middle of an ancient city. It just doesn't fit. So why are the rings so young, and why are they so clean? The rings are made of water ice, almost pure water ice, with only tiny amounts of rocky dust mixed in. That purity is part of what makes them so bright. But space is a dirty place. There's dust floating around, tiny particles of rock and carbon blown off asteroids and comets. Over billions of years, you'd expect that dust to gradually rain down onto the rings, darkening them, making them look older and dirtier. Jupiter's rings, for example, are dark and dusty, which makes sense for rings that have been around for a long time. Saturn's rings should look the same, but they don't. They look fresh, clean, almost newborn. This is the great ring problem, and it's been puzzling scientists for decades. How can Saturn have rings that are so young and so pure in a solar system that's ancient? There are really only two possibilities. Either the rings are constantly being cleaned and refreshed by some unknown process, or they really are young, formed relatively recently in Saturn's history. And if they're young, then something dramatic must have happened to create them. Something that ripped apart a moon or shattered a comet and scattered the debris into those elegant bands we see today. To understand how the rings could form, we need to talk about something called the Roche limit. It's one of the fundamental concepts in planetary science, and it explains why rings exist at all. The Roche limit is the distance from a planet within which tidal forces become stronger than the gravity holding an object together. In other words, it's the point where a planet's gravity will tear apart anything that gets too close. Imagine you're a moon orbiting Saturn. Your own gravity holds you together, keeping all your rocks and ice in a nice solid ball. But you also feel Saturn's gravity pulling on you. And here's the thing, Saturn's gravity doesn't pull evenly. The side of you facing Saturn feels a stronger pull than the side facing away because it's closer to the planet. This difference in gravitational pull is called a tidal force, and it tries to stretch you apart. The concept of tidal forces is something we experience even here on Earth, although usually in a more subtle way. The moon's gravity pulls on Earth, and because the moon is closer to the side of Earth facing it than to the far side, there's a difference in gravitational pull. This difference creates the ocean tides. The water on the side of Earth facing the moon gets pulled toward the moon more strongly than Earth's center, and the water on the far side gets pulled less strongly, so it effectively gets left behind. The result is two bulges of water, one on each side of Earth, and as Earth rotates beneath these bulges, we experience high and low tides. Now imagine scaling this effect up dramatically. Instead of water sloshing around on Earth's surface, imagine an entire moon feeling these tidal forces. If the moon is far enough from the planet, its own gravity is strong enough to hold it together despite the tidal stretching. The moon might feel some stress, might even experience tidal heating if it's in an elliptical orbit that causes the tidal forces to flex and change, but it stays intact. Io, one of Jupiter's moons, experiences extreme tidal heating because Jupiter's massive gravity squeezes and stretches it as it orbits. This tidal heating is so intense that it melts Io's interior and drives the most volcanically active body in the solar system. But Io stays intact because it's outside Jupiter's Roche limit. But move that moon closer and the tidal forces get stronger. The difference in gravity between the near and far sides of the moon increases and the stretching force becomes more intense. Eventually, you reach a point where the tidal forces are stronger than the moon's own gravity. At that point, the moon can't hold itself together anymore. The side facing the planet feels such a strong pull that it starts to break away from the rest of the moon. Cracks form, chunks break off, and the moon disintegrates into a stream of debris. This critical distance is the Roche limit. The exact location of the Roche limit depends on a few factors. It depends on the mass and radius of the planet, because a more massive or larger planet has stronger tidal forces. It also depends on the density and strength of the object being disrupted. A solid, rocky moon can withstand stronger tidal forces than a loose pile of rubble held together only by weak gravity. The Roche limit for a fluid body, something with no internal strength at all, is about 2.4 times the planet's radius. For a solid body with some structural strength, the Roche limit can be somewhat closer, maybe 2 times the planet's radius or even less. For Saturn, with its particular mass and radius, the Roche limit for an icy moon is around 140,000 kilometers from the planet's center. That's about 2.5 Saturn radii. And here's the crucial fact. All of Saturn's main rings, the A, B, and C rings, lie inside this limit. The outer edge of the A ring is about 140,000 kilometers from Saturn's center, right at the Roche limit. Everything inside that boundary can't coalesce into a moon because any object that tried to form would be torn apart by tidal forces. This tells us something profound about the origin of the rings. The ring particles couldn't have just gradually accumulated where they are now, building up over time like snow accumulating on the ground. If particles tried to stick together and form a moon inside the Roche limit, tidal forces would rip the moon apart as soon as it got large enough. The rings must have formed from something that was already assembled, something that formed farther out where tidal forces are weaker and then moved inward, crossing the Roche limit and getting destroyed in the process. We can see this process happening elsewhere in the solar system, although not always with such spectacular results. Comets sometimes pass close to planets, and if they get close enough, they can be torn apart by tidal forces. In 1994, comet Shoemaker-Levy 9 passed within Jupiter's Roche limit and was ripped into more than 20 pieces. These fragments then continued on their orbits and eventually crashed into Jupiter, creating massive impact scars in the planet's atmosphere that were visible for months. This was the first time humans had ever witnessed a collision between 2 solar system bodies, and it dramatically demonstrated the power of tidal forces. Mars has 2 small moons, Phobos and Deimos, and Phobos is slowly spiraling inward toward Mars. Tidal interactions with Mars are draining Phobos' orbital energy, causing it to gradually sink closer to the planet. In about 50 million years, Phobos will cross Mars' Roche limit and be torn apart, creating a ring around Mars. Future astronomers, if there are any observing Mars in 50 million years, will see a ringed planet where now there's just a moon. This is probably a common process in the solar system. Moons form, they migrate, some of them cross the Roche limit, and rings are created. But rings don't last forever. The particles in a ring continue to collide with each other, and these collisions gradually change their orbits. Some particles gain energy and move to higher orbits, while others lose energy and spiral inward toward the planet. Over time, the ring spreads out, becoming more diffuse. Eventually, the inner edge of the ring reaches the planet's atmosphere, and particles start falling in, raining down onto the planet like a slow drizzle of ice and rock. This process is happening to Saturn's rings right now. Cassini measured a steady rain of ring material falling into Saturn's upper atmosphere, about 10,000 kilograms per second. That sounds like a lot, but given the enormous mass of the rings, it means the rings will last for another few 100 million years before they're completely gone. So the rings are temporary. They had a beginning, when a moon crossed the Roche limit and was destroyed, and they'll have an end, when all the particles have either fallen into Saturn or drifted away. We're living in a special time, cosmically speaking, when Saturn has prominent, beautiful rings. In the distant future, or in the distant past before the rings formed, Saturn would have looked much less impressive, just another gas giant without any particular distinguishing features. It's a reminder of how dynamic the solar system is, how nothing stays the same forever, and how lucky we are to be alive at a time when we can witness and study these incredible phenomena. The Roche limit also explains why there's a gap between the rings and Saturn's innermost moons. The rings extend inward to about 74,000 kilometers from Saturn's center, where they meet the planet's outstretched atmosphere. Beyond the outer edge of the A ring at about 140,000 kilometers, there's a region with very few ring particles. And then farther out, at distances greater than 180,000 kilometers, we find Saturn's small inner moons like Prometheus, Pandora, Janus, and Epimetheus. These moons can exist because they're outside the Roche limit. They're still close enough that they feel significant tidal forces, but not close, enough to be torn apart. Their gravity, in turn, affects the rings, creating gaps and sculpting the outer edges of the A and F rings. One of the most fascinating aspects of the Roche limit is that it's not a sharp boundary. It's not like there's a line in space where everything inside is destroyed and everything outside is safe. The reality is more nuanced. Small objects can survive closer to a planet than large objects because the tidal force across a small object is weaker. A grain of dust experiences almost no tidal force because the difference in gravity from one side of the grain to the other is negligible. A house-sized boulder experiences a bit more tidal force, but it might still have enough structural strength to hold together. A kilometer-sized moon, though, would definitely be torn apart if it crossed the Roche limit. This is why Saturn's rings are made of relatively small particles. The process of disruption doesn't just shatter a moon into a few large pieces. It grinds it down into smaller and smaller chunks until each chunk is small enough to survive the tidal forces. As long as you're far enough away, your own gravity is stronger than Saturn's tidal forces, and you stay intact. But if you drift too close, if you cross the Roche limit, the tidal forces win. Saturn's gravity pulls harder on your near side than your far side, and the difference becomes so extreme that you literally get ripped apart. Your moon breaks into chunks, and those chunks get spread out into a ring orbiting the planet. That's how rings form. They're the shattered remains of objects that got too close. Saturn's Roche limit is around 140,000 kilometers from the planet's center, or about 2.5 Saturn radii. All of Saturn's main rings lie inside this limit. That tells us something important. The rings can't have formed from material that slowly accumulated over time. If you tried to build a moon inside the Roche limit, it would just get torn apart by tidal forces before it could grow large enough to hold itself together. The rings must have come from something that formed farther out and then moved inward, crossing the Roche limit and getting destroyed in the process. So what was that something? The leading theory is that it was a moon, a mid-sized moon made mostly of ice. Saturn has dozens of moons, ranging from tiny rocks just a few kilometers across to Titan, a world larger than the planet Mercury. Many of these moons are icy, made of water ice mixed with rock. If one of these moons, perhaps one that was a few hundred kilometers in diameter, somehow spiraled inward and crossed the Roche limit, it would have been torn apart by Saturn's tidal forces. The ice and rock would have shattered into billions of pieces, and those pieces would have spread out into a ring around the planet. This would explain a lot. It would explain why the rings are made of water ice, because the original moon was made of ice. It would explain why the rings are so bright and clean, because the ice was buried inside the moon, protected from space dust and dirt. And it would explain why the rings are so young. If the moon was destroyed relatively recently, within the last 100 million years or so, then the rings are essentially fresh debris, not yet darkened by eons of exposure to space. But this creates another question. Why did a moon spiral inward and get destroyed? Moons don't just randomly fall into their planets. They're held in stable orbits by a balance between their forward motion and the planet's gravity. For a moon to spiral inward, something has to disrupt its orbit. Something has to slow it down or push it off course. There are a few possibilities. Maybe the moon collided with another moon or a comet, and the impact knocked it onto a collision course with Saturn. Maybe tidal interactions with Saturn slowly drained the moon's orbital energy over millions of years, causing it to gradually spiral inward. Or maybe the moon passed too close to one of Saturn's other moons, and the gravitational interaction sent it careening toward the planet. We don't know for sure which scenario is correct, but all of them are plausible. The solar system is a chaotic place, especially in the crowded region around Saturn where dozens of moons orbit in a complex dance. Collisions and close encounters do happen. And once a moon starts spiraling inward, its fate is sealed. It crosses the Roche limit, the tidal forces rip it apart, and the rings are born. This theory also explains another mystery about the rings. They're not uniform. Saturn's rings are divided into several distinct sections labeled with letters in the order they were discovered. The A ring, the B ring, the C ring, and several others, each with its own characteristics. The B ring is the brightest and most massive, containing the bulk of the ring material. The A ring is also bright but separated from the B ring by a gap called the Cassini division, a dark band about 5,000 kilometers wide. The C ring is fainter and more translucent. Then there are faint, dusty rings even farther out, like the E ring and the G ring, which are so faint they can barely be seen. These divisions and gaps are carved by the gravitational influence of Saturn's moons. Some moons orbit right at the edge of a gap, and their gravity shepherds the ring particles, keeping them in line like a cosmic sheepdog. Other moons orbit farther out, but their gravity still reaches into the rings, creating resonances that push particles into certain orbits and clear out others. The result is a series of rings and gaps, each shaped by the gravitational ballet of Saturn's many moons. But even this raises more questions. If the rings were created by a single shattered moon, why are they divided into such distinct sections? Shouldn't they be more uniform? The answer might lie in how the moon broke apart. When an object crosses the Roche limit, it doesn't just explode all at once. It gets stretched and pulled apart gradually. The side facing Saturn feels the strongest tidal forces, so it starts to break apart first, shedding chunks of ice and rock. These chunks spread out into a stream, and as they continue to orbit, they gradually disperse into a ring. But different parts of the original moon might have broken apart, at slightly different times or in slightly different places, creating multiple streams of debris that eventually became the separate rings we see today. Another possibility is that the rings have evolved over time. Even after the moon was destroyed, the ring particles didn't just sit still. They collide with each other, they get pushed around by the gravity of Saturn's moons, and they gradually spread out. Over millions of years, this could cause the ring material to segregate into different bands, with larger particles settling into certain orbits, and smaller particles drifting into others. The gaps would form wherever a moon's gravity clears out a particular region, and the bright rings would form where particles accumulate and collide, grinding each other into fine powder that reflects sunlight brilliantly. So the rings are dynamic, they're not a static structure frozen in time. They're constantly changing, constantly evolving, shaped by collisions and gravity and the slow grind of time. That's part of what makes them so fascinating. They're not just a pretty decoration around Saturn, they're a living record of a cosmic catastrophe, a monument to a moon that once was, and a reminder of the violent forces that shape our solar system. But the rings are just one piece of the Saturn paradox. The planet itself is still a problem. We've talked about how Saturn is less dense than water, how it's made mostly of hydrogen and helium, and how it's still radiating excess heat billions of years after it formed. But we haven't really explained why Saturn is the way it is. Why is it so different from Jupiter? Why is it so light and fluffy when it should be more compressed? And why is it still so active when it should have cooled down long ago? To answer these questions, we need to go back to the beginning, back to the formation of the solar system itself. About 4.5 billion years ago, our corner of the galaxy was nothing but a vast cloud of gas and dust, a nebula floating in the emptiness of space. This nebula was mostly hydrogen and helium left over from the Big Bang, with tiny amounts of heavier elements forged in the hearts of earlier generations of stars. Something happened, maybe a nearby supernova exploded and sent a shockwave through the cloud, and the nebula started to collapse. Gravity pulled the gas and dust together, forming a dense core that would eventually become the Sun. Around this core, the remaining material flattened into a spinning disk, a proto-planetary disk where planets would soon form. In the inner part of the disk, close to the young Sun, it was hot, so hot that only materials with high melting points could remain solid. These were rocky materials like silicates and metals, and they clumped together to form the rocky planets Mercury, Venus, Earth, and Mars. But farther out, beyond what we call the frost line, it was cold enough for water ice and other volatile materials to condense into solid particles. This is where the gas giants formed, in the cold outer reaches of the solar system where ice and gas were abundant. Jupiter and Saturn both formed beyond the frost line, in a region rich in ice and gas. They started as small cores of rock and ice, maybe 10 times the mass of Earth. These cores grew by sweeping up more and more material from the surrounding disk, and as they grew, their gravity became stronger, allowing them to pull in even more material. Eventually, their gravity became so strong that they started capturing hydrogen and helium gas directly from the protoplanetary disk. This is how gas giants are born. They start with a solid core and then they wrap themselves in a massive envelope of gas. But here's the thing, Jupiter and Saturn didn't form in the same place they are now. The early solar system was a chaotic, violent place, and planets didn't just stay where they were born. They migrated. They moved inward and outward, pushed around by gravitational interactions with the protoplanetary disk and with each other. This migration had profound effects on the structure of the solar system, and it's key to understanding why Saturn is the way it is. The story of planetary migration begins with observations of exoplanets, planets orbiting other stars. When astronomers started discovering exoplanets in the 1990s, they found something surprising. Many of these planets were gas giants like Jupiter, but they were orbiting incredibly close to their parent stars, sometimes closer than Mercury orbits our Sun. These so-called hot Jupiters couldn't have formed where they are now. It's too hot that close to a star for ice to condense, and without ice, there's not enough solid material to build the large cores needed to capture gas and become a gas giant. The only explanation was that these planets formed farther out, where it was cold enough for ice to exist, and then migrated inward to their current positions. This discovery revolutionized our understanding of planetary systems. It meant that planets don't necessarily stay where they form. They can move, sometimes over vast distances, and this migration can dramatically reshape a planetary system. The question then became, did migration happen in our solar system too? Did Jupiter and Saturn and the other planets migrate from their formation locations? The answer, according to most planetary scientists, is yes. There's strong evidence that the giant planets in our solar system migrated early in their history. And this migration explains many features of the solar system that otherwise don't make sense. The leading model of this migration is called the Nice model, named after the French city of Nice, where the theory was developed. The Nice model proposes a specific sequence of events that occurred about 600 million years after the solar system formed, during a period called the Late Heavy Bombardment. According to the Nice model, the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, originally formed in different locations than where they are now. Jupiter formed roughly where it is today, but Saturn, Uranus, and Neptune were all closer together, packed into a much more compact region of the outer solar system. Beyond the orbits of these planets was a massive disk of leftover planetesimals, small icy and rocky bodies that didn't get incorporated into planets. This disk was similar to the Kuiper belt we see today, but much more massive, containing hundreds of Earth masses of material. For several 100 million years, this configuration was relatively stable. The planets orbited the Sun, and the disk of planetesimals remained mostly undisturbed beyond them. But then something happened that triggered a cascade of events. Saturn's orbit slowly drifted outward due to gravitational interactions with the planetesimal disk. As Saturn moved outward, its orbital period changed, and eventually Saturn and Jupiter fell into a special gravitational relationship called a mean motion resonance. In this particular resonance, Saturn completed exactly 2 orbits for every 1 orbit Jupiter completed, a 2-to-1 resonance. When planets are in resonance, their gravitational effects on each other repeat in a regular pattern, and this can dramatically amplify their mutual influence. In the case of Jupiter and Saturn, the resonance caused their orbits to become slightly eccentric, more elliptical rather than circular. This might not sound like a big deal, but it had enormous consequences. As Jupiter and Saturn's orbits became eccentric, they started plowing into the inner edge of the planetesimal disk. Their gravity scattered these planetesimals in all directions, like a pair of bulldozers crashing through a field of boulders. Some of the scattered planetesimals were flung inward toward the Sun, where they collided with the inner rocky planets and the forming terrestrial moons. This is what caused the Late Heavy Bombardment, a period of intense impacts that occurred about 4 billion years ago. The evidence for this bombardment is written in the cratered surfaces of the Moon, Mercury, and Mars. These worlds are covered in craters from ancient impacts, and when scientists dated the rocks brought back from the Apollo missions, they found that many of the largest craters on the Moon formed during a relatively short period about 4 billion years ago. This bombardment also affected Earth, although most of the evidence has been erased by plate tectonics and erosion. Other planetesimals were flung outward beyond the orbits of the giant planets. Some of these objects ended up in the Kuiper Belt, the region of space beyond Neptune where Pluto and thousands of other small icy bodies orbit today. Others were flung even farther into the Oort cloud, a vast spherical shell of comets that surrounds the solar system at distances of tens of thousands of astronomical units. The Oort cloud is so far away that objects there are barely bound to the Sun, and they can be perturbed by the gravity of passing stars, sending them on long plunges through the inner solar system where they become visible as long-period comets. But the scattering of planetesimals also affected the giant planets themselves. Every time a planet ejects a planetesimal outward, giving it energy, the planet loses a bit of energy and moves slightly inward. Every time a planet captures a planetesimal inward, taking energy from it, the planet gains energy and moves slightly outward. For Jupiter, which is so massive that it mostly scattered planetesimals inward toward the Sun, the net effect was a small inward migration. For Saturn, Uranus, and Neptune, which interacted more with planetesimals in the outer disk, the net effect was outward migration. Saturn, Uranus, and Neptune all moved farther from the Sun, spreading out into the configuration we see today. This migration was not smooth or gentle. As the planets moved through the planetesimal disk, they interacted with each other gravitationally, and these interactions caused their orbits to change unpredictably. Uranus and Neptune, in particular, may have switched positions or crossed paths during this chaotic period. There's even some evidence suggesting that there might have been a fifth giant planet that was ejected from the solar system entirely during this upheaval, flung into interstellar space by a close encounter with Jupiter. For Saturn specifically, the migration had several important effects. First, it determined Saturn's final orbital distance from the Sun. Saturn ended up settling at about 9.5 astronomical units from the Sun, a distance where it's been relatively stable for the past 4 billion years. Second, the migration affected Saturn's interior structure and thermal evolution. The gravitational interactions during migration would have stirred Saturn's interior, mixing different layers and potentially depositing energy deep inside the planet. This could help explain why Saturn is still radiating excess heat billions of years later. The planet might still be slowly releasing energy that was deposited during the violent migration period. Third, the migration affected Saturn's moons. Before the migration, Saturn probably had a different family of moons than it has today. Some of Saturn's original moons might have been lost during the chaos, either ejected from the system or destroyed in collisions. Other moons might have been captured during the migration, as Saturn passed through the planetesimal disk and gravitationally captured some of the objects it encountered. This could explain why some of Saturn's outer moons have strange, highly inclined, or retrograde orbits. They're not native to the Saturn system, they're captured interlopers, former denizens of the planetesimal disk that got swept up by Saturn's gravity during the migration. The migration also had more subtle effects on Saturn's satellites. Tidal interactions between Saturn and its moons would have changed during and after the migration, potentially causing some moons to migrate inward or outward over time. This could be relevant to the formation of the rings. If one of Saturn's mid-sized moons was pushed inward by tidal interactions, either during the late heavy bombardment or more recently, it might have eventually crossed the Roush limit and been torn apart, creating the rings we see today. The Nice model isn't the only migration scenario that planetary scientists have proposed, but it's one of the most successful at explaining the architecture of the outer solar system. It explains why Jupiter is where it is, why Saturn is where it is, why Uranus and Neptune are so far out, and why the Kuiper Belt has the structure it does. It also explains the late heavy bombardment and the cratering patterns we see on the inner planets and moons, and it provides a framework for understanding how Saturn evolved to its current state. But there's another, even more dramatic migration event that might have occurred earlier in the solar system's history, before the Nice model migration. This event is called the Grand Tack, and it involves Jupiter migrating inward toward the Sun, and then reversing direction and migrating back outward. The Grand Tack hypothesis was proposed to explain some puzzling features of the inner solar system, particularly the small size of Mars and the structure of the asteroid belt. According to the Grand Tack scenario, Jupiter formed quickly within the first few million years of the solar system's existence. As Jupiter grew, it interacted with the gas in the protoplanetary disk, and these interactions caused Jupiter to migrate inward toward the Sun. Jupiter spiraled inward until it reached an orbital distance of about 1.5 astronomical units, roughly where Mars is today. At this point, Jupiter's migration was causing havoc in the inner solar system, disrupting the orbits of forming rocky planets and scattering planetesimals everywhere. But then Saturn finished forming. Saturn had been growing more slowly than Jupiter because it formed farther out, where the disk was less dense, but eventually it reached a size where it, too, started migrating inward. Saturn followed Jupiter's path, moving toward the Sun. And when Saturn caught up to Jupiter, something remarkable happened. The two planets became locked in a mean motion resonance, and the dynamics of their interaction with the disk changed completely. Instead of both planets continuing to migrate inward, the resonance caused them to stop and reverse direction. Jupiter and Saturn began migrating outward, back toward the outer solar system. This outward migration is what gives the Grand Tack its name, after the sailing maneuver of tacking, changing direction to sail against the wind. Jupiter and Saturn tacked, reversing their inward journey and heading back out. As they migrated outward, they scattered material in their path, clearing out much of the inner solar system and preventing a large planet from forming in what is now the asteroid belt. They also truncated the growth of Mars, which explains why Mars is so much smaller than Earth and Venus. Mars had started forming, but before it could grow to a larger size, Jupiter's migration disrupted the local disk of material, leaving Mars as a stranded embryo, a planet that never finished growing. The Grand Tack, if it occurred, would have been even more violent and dramatic than the Nice model migration. It happened much earlier, when the solar system was still full of gas and dust, and it reshaped the entire inner solar system. For Saturn, the Grand Tack would have been a defining moment. The planet formed in one location, migrated inward through the protoplanetary disk, experienced the intense gravitational interaction with Jupiter, and then migrated back outward to a completely different location. This journey would have affected every aspect of Saturn's structure and evolution, from its interior composition to its satellite system. Both of these migration events, the Grand Tack and the Nice model migration, paint a picture of a solar system that was far more dynamic and chaotic than the orderly arrangement of planets we see today. The planets didn't just form in their current locations and sit there for billions of years. They moved, they interacted, they scattered debris, and they reshaped the solar system multiple times over. And Saturn, as a participant in both of these migrations, carries the scars and signatures of this violent history in its structure, its moons, and its improbably beautiful rings. Jupiter formed first because it was closer to the Sun, where the disk was denser and there was more material to work with. It grew quickly, becoming a massive giant that dominated the outer solar system. Saturn formed farther out in a region where the disk was less dense and there was less material available. That's part of why Saturn is smaller than Jupiter. It formed in a less favorable location. But then something happened. The planets started to migrate. Migration happens because of gravitational interactions between a planet and the disk, of gas and dust around it. When a planet moves through the disk, it pushes material around, creating waves and spirals in the gas. These waves carry momentum, and they can pull on the planet, either speeding it up or slowing it down. If the planet is slowed down, it loses orbital energy and spirals inward toward the sun. If it's sped up, it gains energy and moves outward. The direction of migration depends on the details of how the planet interacts with the disk. But for large planets like Jupiter and Saturn, the most common outcome is inward migration. They spiral toward the sun. Jupiter started migrating inward, moving closer to the sun and disrupting the orbits of everything in its path. As Jupiter moved, its gravity stirred up the inner solar system, scattering asteroids and smaller bodies, preventing a planet from forming in what is now the asteroid belt. But then Saturn caught up. Saturn was also migrating inward, following Jupiter's path. And when Saturn got close enough to Jupiter, something remarkable happened. The two planets became locked in a gravitational resonance. A resonance is a special relationship between the orbits of two objects, where their orbital periods form a simple numerical ratio, like 2:1 or 3:2. When planets are in resonance, their gravitational tugs on each other repeat in a regular pattern, and this can have powerful effects on their orbits. In the case of Jupiter and Saturn, the resonance changed the direction of their migration. Instead of continuing to spiral inward, they started moving outward, away from the sun. Jupiter and Saturn essentially bounced off each other and headed back, out into the outer solar system. This outward migration is known as the grand tack, named after the way a sailboat tacks back and forth to sail against the wind. The grand tack had huge consequences for the solar system. As Jupiter and Saturn moved outward, they plowed through the region where Uranus and Neptune were forming. Their gravity scattered smaller bodies in all directions, sending some crashing into the inner solar system and others out into the far reaches of the solar system, forming the Kuiper belt and the Oort cloud. This period of chaos is called the Late Heavy Bombardment, and it left scars on every rocky planet and moon in the inner solar system, including Earth's moon, which is covered in craters from this violent time. But for Saturn, the migration had another effect. It determined where Saturn ended up and how its interior structure developed. Because Saturn formed farther out and migrated in a different way than Jupiter, it ended up with a different internal structure. Saturn's core is smaller than Jupiter's, and it has less liquid metallic hydrogen, which is why Saturn is less dense overall. The migration also affected how Saturn cooled and evolved over time. The gravitational interactions during migration would have stirred up Saturn's interior, mixing heat and changing how the planet radiated energy. This could explain why Saturn is still so warm and active today, billions of years later. It's not just slowly cooling from its initial formation, it's still recovering from the chaos of migration, still settling into its final state. This brings us to another strange feature of Saturn. Deep inside the planet, beneath the visible clouds and the layers of hydrogen gas, the pressure is so intense that hydrogen behaves in ways that would seem impossible on Earth. As you go deeper into Saturn, the pressure increases and the hydrogen gets compressed. First, it becomes a liquid, no longer a gas, but a dense fluid. Go deeper still, and the pressure becomes so extreme that the hydrogen transforms into liquid metallic hydrogen. Liquid metallic hydrogen is one of the strangest substances in the universe. Under normal conditions, hydrogen is a simple molecule made of two hydrogen atoms bonded together. It's a gas, and it doesn't conduct electricity. But when you compress hydrogen to extreme pressures, millions of times the atmospheric pressure on Earth, something extraordinary happens. The molecules break apart and the hydrogen atoms get squeezed so close together that their electrons start to move freely between atoms like electrons in a metal. The hydrogen becomes a liquid that conducts electricity, a liquid metal. This liquid metallic hydrogen exists in the deep interiors of both Jupiter and Saturn, and it's responsible for their powerful magnetic fields. As the planet rotates, the liquid metallic hydrogen swirls and flows, creating electric currents. These currents generate a magnetic field, just like the electric currents in Earth's iron core generate Earth's magnetic field. Saturn's magnetic field is weaker than Jupiter's, partly because Saturn has less liquid metallic hydrogen, but it's still strong enough to trap charged particles from the sun and create beautiful auroras at Saturn's poles, shimmering curtains of light that dance across the planet's upper atmosphere. But even the existence of liquid metallic hydrogen inside Saturn raises questions. The pressure required to create this state of matter is immense, and it only exists deep inside the planet where the weight of all the overlying layers compresses the hydrogen to impossible densities. In Saturn's case, the transition to liquid metallic hydrogen happens at a depth where the pressure is about 1,000,000 times Earth's atmospheric pressure. Above that depth, the hydrogen is still liquid but not metallic. Below that depth, it's liquid metal, and right at the transition zone, there's a boundary where the properties of hydrogen change dramatically. This boundary is important because it affects how heat moves through Saturn's interior. Heat generated in the core, whether from leftover formation energy or from gravitational contraction, has to travel outward to the surface to be radiated into space. In the liquid metallic hydrogen zone, heat moves relatively efficiently because the liquid can flow and carry heat with it, a process called convection. But at the transition zone, things get complicated. The properties of hydrogen change, and that can slow down the flow of heat. Some scientists think this transition zone might act like a blanket, trapping heat inside Saturn and preventing it from escaping as quickly as it should. That could help explain why Saturn is still so warm after billions of years. There's another possibility too. Deep inside Saturn, there might be something unexpected happening with helium. Remember, Saturn is mostly hydrogen, but it also has a lot of helium, about 3 to 4% of the planet's mass. On Earth, that might not sound like much, but in a planet the size of Saturn, that's still an enormous amount of helium. And helium doesn't always play nicely with hydrogen under extreme conditions. When the pressure and temperature are just right, helium can start to separate from hydrogen, like oil separating from water. The helium droplets are denser than the surrounding hydrogen, so they sink toward the core, raining down through the liquid hydrogen like drops of mercury. This process is called helium rain, and it has two important effects. First, it releases gravitational energy. As the helium droplets fall, they convert potential energy into heat, just like a falling object releases energy when it hits the ground. This heat adds to Saturn's internal energy budget, helping to explain why the planet is still radiating more heat than it should. Second, helium rain changes the composition of Saturn's outer layers. As helium sinks toward the core, the upper layers of the planet become depleted in helium and enriched in hydrogen. This affects how the planet cools and how heat moves through its interior. It might also help explain why Saturn is less dense than Jupiter. If Saturn has less helium in its outer layers and more of it concentrated in the core, then the overall density would be lower. Jupiter, being more massive and having higher internal pressures, might not experience as much helium rain, or it might have already completed this process billions of years ago. Saturn, on the other hand, might still be in the middle of it, slowly raining helium into its core and radiating the excess heat into space. All of this paints a picture of Saturn as a planet that's still very much alive, still evolving, still changing. It's not a dead, cold world that formed billions of years ago and then just sat there. It's an active, dynamic planet with a complex interior structure, a powerful magnetic field, and a history of violent migration and gravitational chaos. The fact that Saturn is less dense than water, the fact that it's still radiating excess heat, the fact that it has such young and pristine rings, all of these things are connected. They're all consequences of Saturn's formation, its migration, and the ongoing processes happening deep inside the planet. But there's one more piece of the puzzle we need to talk about, and that's Saturn's atmosphere. When you look at Saturn through a telescope, what you see is the planet's upper atmosphere, a layer of clouds and haze that covers the entire globe. These clouds are not made of water like Earth's clouds. They're made of ammonia ice and other exotic materials, and they're whipped into bands and swirls by Saturn's incredibly fast winds. Saturn rotates very quickly, completing a full rotation in just 10.5 hours. That's fast for a planet, and it means the equator is moving at speeds of over 1,000 kilometers per hour. This rapid rotation, combined with the planet's internal heat, drives powerful winds that can reach speeds of up to 1,800 kilometers per hour, faster than the speed of sound on Earth. The structure of Saturn's atmosphere is layered, with different compounds condensing at different altitudes depending on temperature and pressure. At the very top of the visible atmosphere, about 50 kilometers above the main cloud deck, There's a layer of haze made of tiny particles of hydrocarbons. These hydrocarbons are created when sunlight breaks apart methane molecules in the upper atmosphere, and the resulting fragments recombine into more complex molecules like ethane, acetylene, and propane. This haze gives Saturn a slightly yellowish color, although Saturn is generally much less colorful than Jupiter. Below the haze layer, we reach the main cloud deck. The uppermost clouds are made of ammonia ice, crystalline particles of frozen ammonia suspended in the atmosphere. These ammonia clouds are the brightest and most reflective features on Saturn, and they create the light-colored zones we see in images of the planet. The temperature at this level is around minus 130 degrees Celsius, cold enough for ammonia to freeze out of the gas phase and form ice crystals. Go deeper, and you reach a layer where ammonium hydrosulfide clouds form. Ammonium hydrosulfide is a compound made of ammonia and hydrogen sulfide, and it condenses into clouds at slightly higher temperatures and pressures than pure ammonia. These clouds are probably brownish or yellowish in color, although we can't see them directly because they're hidden beneath the ammonia cloud layer. The ammonium hydrosulfide clouds contribute to the darker belts on Saturn, the regions where we're seeing slightly deeper into the atmosphere. Deeper still, about 100 kilometers below the top of the ammonia clouds, there's a layer of water clouds. Yes, water clouds, just like on Earth, made of droplets of liquid water and ice crystals. The temperature at this level is around 0 degrees Celsius, the freezing point of water. This is where most of Saturn's weather actually happens. The water clouds are where convection is strongest, where warm, moist air rises from deeper in the atmosphere, cools and condenses into clouds, releasing latent heat that drives further convection. This is the engine that powers Saturn's storms and lightning. The existence of water deep in Saturn's atmosphere is important because it tells us about the planet's bulk composition and formation history. Water is a key ingredient in the icy materials that made up the building blocks of Saturn's core. The fact that there's water vapor in Saturn's atmosphere and that it condenses into clouds means that water from the planet's interior is being cycled through the atmosphere by convection. This gives us a window into the planet's deep interior, allowing us to infer things about the composition and structure of layers we can never directly observe. Saturn's wind patterns are organized into alternating bands of eastward and westward flow, parallel to the equator. These bands are called jets, and they're similar to the jet streams in Earth's atmosphere, although much faster and more stable. Saturn has about a dozen distinct jets, 6 in each hemisphere, and each jet maintains its speed and position for years or even decades. The fastest winds on Saturn blow in the equatorial jet, reaching speeds of about 1,800 kilometers per hour. These are among the fastest winds measured on any planet in the solar system, faster even than Jupiter's winds. What drives these incredibly fast winds is still something of a mystery. On Earth, jet streams are driven by temperature differences between the equator and the poles, combined with Earth's rotation. The same basic mechanism probably operates on Saturn, but there are important differences. On Earth, the sun is the primary heat source, warming the surface and creating temperature gradients. On Saturn, the internal heat is at least as important as sunlight, and this internal heat is distributed fairly evenly across the planet's surface. There's no solid surface to absorb sunlight preferentially at the equator, and the rapid rotation means that heat gets spread around quickly. So the temperature difference between Saturn's equator and poles is much smaller than on Earth, yet the winds are much faster. This suggests that Saturn's internal heat and the convection it drives plays a major role in powering the winds. The jet streams on Saturn also show remarkable stability. Unlike Earth's jet streams, which meander and change strength seasonally, Saturn's jets stay in more or less the same place year after year. This stability might be related to the depth of the jets. On Earth, jet streams are shallow features confined to the upper few kilometers of the atmosphere. On Saturn, there's evidence that the jets might extend much deeper, perhaps hundreds of kilometers down into the atmosphere. If the jets are rooted deep in the planet's interior, they would be less susceptible to changes at the surface and more stable over time. Saturn also experiences vortices, circular storm systems similar to hurricanes or cyclones on Earth. Some of these vortices are long-lived, persisting for months or years, while others are short-lived, forming and dissipating within days or weeks. The most famous feature on Saturn is a massive storm at the North Pole, a hexagonal-shaped jet stream that surrounds a central vortex. This hexagon was first observed by the Voyager spacecraft in the 1980s, and it's been continuously present ever since. The hexagon is about 30,000 kilometers across, large enough to fit 4 Earths inside, and its sides are each about 14,000 kilometers long, longer than the diameter of Earth. The hexagon is a standing wave pattern in the jet stream created by the interaction between the winds and the rotation of the planet. Each corner of the hexagon is a region where the wind speed changes, creating a kink in the jet stream. The pattern is stable because the wave speed matches the rotation rate of the planet at that latitude, causing the hexagon to rotate with Saturn and maintain its shape. It's a beautiful example of how fluid dynamics can create geometric patterns, and it's unique in the solar system. No other planet has a hexagonal polar vortex like Saturn's. At the center of the hexagon, there's a massive hurricane-like vortex with an eye about 2,000 kilometers across. This eye is similar to the eye of a hurricane on Earth, a region of relative calm surrounded by intense winds. The winds around the eye reach speeds of about 500 kilometers per hour, and the vortex extends deep into Saturn's atmosphere. Images from Cassini show that the eye has a well-defined structure, with towering clouds surrounding a clear central region. It's a permanent fixture of Saturn's North Pole, a storm that's been raging for at least several decades and possibly much longer. Saturn's South Pole also has a large vortex, although it doesn't have a hexagonal pattern. The South Polar Vortex is more circular and shows features similar to the eye of a terrestrial hurricane. Like the North Polar Vortex, it's a deep, long-lived storm system driven by convection and the planet's rotation. The presence of these large, stable vortices at both poles suggests that polar storms are a fundamental feature of Saturn's atmospheric dynamics, probably driven by the combination of the planet's rapid rotation and the distribution of internal heat. In addition to these large, permanent features, Saturn experiences episodic storms that can grow to enormous sizes. The most dramatic of these are the Great White Spots, massive convective storms that erupt in Saturn's northern hemisphere, about once every 30 years, or roughly once per Saturn year. These storms are thought to be triggered by seasonal changes. Saturn's axis is tilted at about 27 degrees, similar to Earth's tilt, so the planet experiences seasons as it orbits the Sun. Each season lasts about 7.5 Earth years. When spring comes to Saturn's northern hemisphere, the increased sunlight warms the upper atmosphere, creating instabilities that can trigger massive convective storms. The most recent Great White Spot erupted in December of 2010 in Saturn's northern hemisphere. It started as a small, bright cloud that was initially noticed by amateur astronomers. Within weeks, the storm had grown into a massive system that wrapped around the entire planet, leaving a trail of turbulent clouds in its wake. At its peak, the storm was large enough to be visible through small telescopes from Earth, appearing as a bright white oval against Saturn's pale yellow disk. The storm was so powerful that it disrupted the normal jet stream patterns, changed the temperature of the upper atmosphere by several degrees, and was accompanied by intense lightning activity deep in the atmosphere. Cassini's instruments detected radio signals from the lightning, allowing scientists to track the storm's evolution in real time. The lightning on Saturn is much more powerful than lightning on Earth, with individual flashes releasing energies equivalent to thousands of terrestrial lightning bolts. This intense lightning is generated in the water cloud layer, about 100 kilometers below the visible cloud tops, where strong convection creates charge separation and electrical discharge. The radio waves from the lightning can penetrate through the overlying clouds and be detected by spacecraft and even by radio telescopes on Earth. The Great White Spot of 2010 lasted for about 7 months before finally dissipating. During that time, it stirred up the atmosphere, mixed different layers, and deposited a trail of altered clouds that took years to fade away. Scientists studying the storm learned a great deal about Saturn's atmospheric dynamics, including how convection works on a giant planet, how storms can tap into the planet's internal heat, and how seasonal changes can trigger massive weather events. But Saturn's atmosphere isn't just about storms and winds, it's also a complex chemical laboratory where hundreds of different reactions are taking place. In the upper atmosphere, sunlight drives photochemistry, breaking apart molecules and creating new compounds. Methane, for example, is broken apart by ultraviolet light from the sun, creating reactive fragments that can recombine into more complex hydrocarbons. Over time, this process creates a haze of organic molecules that gives Saturn its subtle color and contributes to the planet's heat budget by absorbing sunlight. Deeper in the atmosphere, in the water cloud layer, there are different chemical processes at work. Lightning generates high temperatures and pressures that can drive chemical reactions, creating compounds that wouldn't normally form in Saturn's cold atmosphere. Water, ammonia, methane, and other simple molecules can be broken apart and recombined into more complex species. Some of these reactions might even create prebiotic molecules, the building blocks of life, although Saturn itself is far too cold and dynamic to support life as we know it. The chemistry of Saturn's atmosphere also varies with latitude and season. Near the equator, where sunlight is more direct, photochemistry is more active, creating more haze and changing the composition of the upper atmosphere. Near the poles, where sunlight is weaker, the atmosphere is clearer and less chemically active, at least in the upper layers. But the polar vortices bring material up from deeper in the atmosphere, exposing gases and particles that wouldn't normally reach the upper atmosphere. This creates opportunities for unique chemistry and allows scientists to probe the composition of Saturn's deeper layers. These winds create the banded structure you see on Saturn, alternating light and dark bands that circle the planet parallel to the equator. The light bands, called zones, are regions where gas is rising from deeper in the atmosphere, bringing fresh ammonia ice crystals that reflect sunlight brightly. The dark bands, called belts, are regions where gas is sinking back down, exposing darker, deeper layers of the atmosphere. The whole system is a giant convection pattern, with hot gas rising, cooling, and sinking back down, driven by the planet's internal heat. But Saturn's atmosphere is relatively calm compared to Jupiter's. Jupiter's atmosphere is full of massive storms, including the famous Great Red Spot, a hurricane that's been raging for at least 150 years and is large enough to swallow Earth whole. Saturn has storms too, but they're generally smaller and shorter-lived. That might seem surprising given how much energy is flowing through Saturn's atmosphere, but it's probably related to Saturn's lower internal heat output. Jupiter radiates more excess heat than Saturn, and that extra energy drives more violent weather. Saturn, with its slightly cooler interior, has a somewhat calmer atmosphere. That said, Saturn does occasionally produce spectacular storms. About once every 30 years, as Saturn orbits the Sun, a massive storm erupts in the northern hemisphere. These storms are called Great White Spots, and they can grow to be thousands of kilometers across, visible even through small telescopes from Earth. The last Great White Spot appeared in 2010 and lasted for several months. It started as a small bright cloud and grew into a massive storm system that wrapped around the entire planet, leaving a trail of turbulent clouds in its wake. The storm was so powerful that it disrupted the planet's jet streams and affected the atmospheric temperature and composition. These great white spots are thought to be caused by seasonal changes on Saturn. Because Saturn's axis is tilted, the planet experiences seasons just like Earth does, although each season lasts about 7.5 years because Saturn takes 30 years to orbit the Sun. When spring comes to Saturn's northern hemisphere, the increased sunlight warms the upper atmosphere, creating instabilities that can trigger these massive storms. It's a reminder that even though Saturn is a cold, distant world, it's still subject to the same basic physics that governs weather on Earth. Sunlight heats the atmosphere, heat drives convection, and convection creates storms. Saturn's atmosphere also contains a surprising variety of chemicals. In addition to hydrogen, helium, and ammonia, there are traces of methane, water vapor, phosphine, and various hydrocarbons. These chemicals are produced by a combination of processes. Some of them come from the deep interior, brought up by convection. Others are created by chemical reactions in the upper atmosphere, driven by sunlight and lightning. Saturn has lightning, lots of it, although it's different from Earth's lightning. On Saturn, lightning occurs deep in the atmosphere, in the water cloud layer far below the visible surface. The lightning flashes are so bright that they can be detected even though they're buried beneath hundreds of kilometers of clouds. The chemistry in Saturn's atmosphere is complex, and scientists are still working to understand all the reactions that take place there. Some of these reactions produce unusual compounds that don't exist naturally on Earth, exotic molecules that can only form under the extreme conditions found in Saturn's atmosphere. Studying these chemicals helps us understand not just Saturn, but also the processes that might occur on exoplanets, planets orbiting other stars, many of which are thought to be gas giants similar to Saturn and Jupiter. All of this complexity, the bands and storms, the exotic chemistry, the lightning and winds, it all comes from the same basic source: heat. Saturn's internal heat, left over from formation and augmented by gravitational contraction and possibly helium rain, drives the entire atmospheric system. Without that heat, Saturn would be a cold, dead world with no weather, no storms, no movement. But because Saturn is still warm, still active, the atmosphere is alive with motion and energy. It's a planetary heat engine converting thermal energy into wind and weather, and it's been running for billions of years. But let's circle back to the big picture, to the question we started with. Why does Saturn exist at all? Why is it so different from Jupiter? Why does it have these incredible rings and this bizarre low density and all these strange features that don't quite fit our models? The answer, as we've seen, is complicated. It's not just one thing, it's a combination of factors, all working together, all connected to Saturn's history and evolution. Saturn exists because it formed in a specific place at a specific time, in the outer solar system where ice and gas were abundant. It grew large enough to capture a massive envelope of hydrogen and helium, but it didn't grow quite as large as Jupiter because it formed farther out, where the protoplanetary disk was less dense. Then it migrated, pushed and pulled by gravitational interactions with Jupiter and the disk, ending up in its current orbit. That migration shaped Saturn's internal structure, mixed its interior, and may have kept it warmer than it would otherwise be. The rings exist because at some point, probably relatively recently in cosmic terms, a moon got too close and crossed the Roche limit. Tidal forces tore the moon apart and the debris spread out into the beautiful ring system we see today. The rings are young and pristine because they're fresh debris, not yet darkened by eons of exposure to space dust. And they're still there because they're stable, held in place by the gravity of Saturn and its many other moons. Saturn's low density is a result of its composition and structure. It's made of the lightest elements, hydrogen and helium, and it has less liquid metallic hydrogen than Jupiter because it's less massive and has lower internal pressures. Helium rain might be concentrating helium in the core, further reducing the density of the outer layers. And Saturn's ongoing warmth, its excess heat radiation, is a combination of leftover formation energy, gravitational contraction, and possibly helium rain, releasing energy as it falls toward the core. All of these pieces fit together into a picture of Saturn as a planet that's the product of a violent, chaotic history. The early solar system wasn't a peaceful place where planets formed in neat rows and stayed where they were born. It was a cosmic demolition derby, with planets migrating, colliding, and scattering debris in all directions. Saturn is a survivor of that chaos, a giant planet that migrated through the outer solar system, wreaking havoc along the way, and ended up in an orbit that's been stable for billions of years. And here's the beautiful part. Saturn's impossibility is what makes it so fascinating. If Saturn had formed exactly where it is now and never moved, if it had cooled down and become a cold, dead world, if its rings had never formed, then Saturn would just be a smaller, less interesting version of Jupiter. But because of all these unusual features, all these paradoxes and mysteries, Saturn stands out. It's unique. It's a planet that challenges our understanding of how planets work, and in doing so, it teaches us more about the universe. Saturn's rings are a cosmic accident, a monument to a shattered moon, and they won't last forever. Over millions of years, the ring particles will slowly spiral inward, raining down onto Saturn's atmosphere. Eventually, the rings will disappear, and Saturn will become just another gas giant, ringless and less remarkable. But for now, in this brief moment in cosmic history, we get to witness Saturn in all its glory, with its rings shining bright and its storms raging and its mysteries still unsolved. There's something poetic about that. Saturn exists on a knife edge between what's possible and what's not. It's too light to make sense, too warm to be this old, and too beautiful to be an accident. But it is. It's all an accident, a series of unlikely events that happen to produce this particular planet in this particular place at this particular time. And we're lucky enough to be here to see it. Saturn, reminds us that the universe is full of surprises, full of phenomena that don't fit neatly into our theories and models. Every time we think we understand how planets form and evolve, we discover something new, something unexpected that forces us to revise our ideas. Saturn has been doing that to scientists for centuries. When Galileo first pointed his telescope at Saturn in 1610, he saw something strange but couldn't quite make out what it was. He thought Saturn had ears or handles on either side. It took decades before better telescopes revealed that those handles were actually rings. And ever since then, Saturn has been challenging us, revealing new mysteries with every observation. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, revolutionized our understanding of the planet and its moons. Cassini's instruments measured the rings in exquisite detail, analyzed the composition of Saturn's atmosphere, studied the planet's magnetic field, and discovered new moons and unexpected phenomena. The data from Cassini will keep scientists busy for decades, uncovering new insights into how Saturn works and how it came to be. One of Cassini's most important findings was about the age of the rings. By measuring how much material is in the rings and how quickly they're being contaminated by dust, scientists were able to estimate that the rings are probably between 10 million and 100 million years old. That's young, cosmically speaking, but it's also a problem. If the rings are that young, then they formed during the age of the dinosaurs or even more recently, long after the solar system settled into its current configuration. What could have caused a moon to break apart so recently? We don't know for sure, but it's a reminder that even in a solar system that's billions of years old, dramatic events can still happen. The universe is never truly stable. Cassini also discovered that Saturn's magnetic field is almost perfectly aligned with its rotation axis, which is unusual. Most planets, including Earth and Jupiter, have magnetic fields that are tilted relative to their rotation axis. Saturn's alignment is so precise that it's hard to explain. It might be related to the structure of Saturn's interior, to the way liquid metallic hydrogen flows and generates the magnetic field. Or it might be a sign of something we don't yet understand about how magnetic fields work in gas giants. Either way, it's another piece of the Saturn puzzle. And then there are Saturn's moons. Saturn has at least 82 known moons, and probably many more small ones that haven't been discovered yet. These moons are incredibly diverse. Titan, the largest, is bigger than Mercury and has a thick atmosphere and lakes of liquid methane on its surface. Enceladus, a tiny, icy moon, has geysers that shoot water vapor and ice particles into space, creating one of Saturn's faint outer rings. Iapetus has a bizarre two-tone appearance, with one hemisphere bright and icy and the other dark and mysterious. And then there are dozens of smaller moons, some of which are probably captured asteroids or comets, others that formed along with Saturn in the protoplanetary disk. Let's talk about Titan first, because it's one of the most fascinating objects in the entire solar system. Titan is the only moon in the solar system with a substantial atmosphere, and that atmosphere is thicker than Earth's. The surface pressure on Titan is about 1.5 times Earth's sea level pressure. The atmosphere is mostly nitrogen, just like Earth's, but instead of oxygen, it has methane and a complex mixture of organic compounds. The temperature on Titan's surface is about minus 180 degrees Celsius, cold enough that water ice is as hard as rock and methane can exist as a liquid. And Titan does have liquid methane, lots of it. Cassini discovered that Titan's surface is covered with lakes and seas of liquid hydrocarbons, mostly methane and ethane. These lakes are concentrated near the poles, where the temperature is slightly cooler and methane rain is more common. The largest of these seas, Kraken Mare, is bigger than the Caspian Sea on Earth, and it's filled with liquid methane mixed with dissolved nitrogen and other gases. Radar images from Cassini show that these lakes have shorelines, inlets, and islands, just like lakes on Earth. There are even river channels carved by flowing methane, creating drainage networks that carry liquid from the highlands to the lowlands. Titan's atmosphere is constantly being replenished with methane from the surface. Without this replenishment, sunlight would break down all the methane in the atmosphere within about 10 million years, converting it into more complex hydrocarbons that rain down onto the surface. The fact that there's still methane in Titan's atmosphere means there must be a source, a reservoir of methane either on or below the surface that releases gas into the atmosphere. Some scientists think this reservoir might be a subsurface ocean of liquid, water mixed with ammonia beneath the icy crust. Methane from deep in Titan's interior could be released through volcanic activity, although Titan's volcanoes would erupt liquid water and ammonia rather than molten rock. Titan is also covered in organic molecules, the building blocks of life. These organics are created in the upper atmosphere by photochemistry, as sunlight breaks apart methane and nitrogen molecules and the fragments recombine into more complex compounds. Over time, these organics settle out of the atmosphere and accumulate on the surface, creating a layer of reddish-brown sludge that covers much of the moon. Some of these organic molecules are similar to the precursors of life on early Earth, which has led to speculation that Titan might harbor some form of life, although any life on Titan would have to be based on radically different chemistry than life on Earth. Then there's Enceladus, a small moon only about 500 kilometers in diameter, smaller than the length of Great Britain. Despite its small size, Enceladus is one of the most geologically active bodies in the solar system. In 2005, Cassini discovered that Enceladus has geysers erupting from cracks near its south pole, shooting plumes of water vapor, ice particles, and organic molecules into space. These plumes reach heights of hundreds of kilometers above the surface, and some of the material escapes Enceladus's weak gravity entirely, going into orbit around Saturn and creating the faint E-ring. The discovery of these geysers was a complete surprise. Enceladus is so small that it should have frozen solid billions of years ago, becoming a dead, inert ball of ice. But instead, it's warm and active, with liquid water beneath its icy crust. The source of this heat is tidal friction. Enceladus orbits Saturn in a slightly elliptical orbit, and as it moves closer to and farther from Saturn, the planet's gravity squeezes and stretches the moon. This constant flexing generates heat, just like bending a paperclip back and forth makes it warm. The heat melts ice in Enceladus's interior, creating a subsurface ocean of liquid water that feeds the geysers. Cassini flew through the plumes of Enceladus multiple times, analyzing their composition with its instruments. The results were astonishing. The plumes contain water vapor, ice particles, salt, organic molecules, and even molecular hydrogen. The presence of salt indicates that the water comes from a salty ocean, similar to Earth's oceans. The organic molecules include complex hydrocarbons and compounds containing nitrogen, suggesting that the ocean might have the chemical ingredients necessary for life. And the molecular hydrogen suggests that there are chemical reactions occurring at the ocean floor, where warm water interacts with rocky material, potentially providing energy that could support microbial life. Enceladus has become one of the top targets for future astrobiology missions. It has liquid water, organic molecules, and a source of energy, the three key ingredients thought to be necessary for life. The fact that the ocean is venting its contents into space through the geysers means that we might be able to detect signs of life without even landing on the moon. A spacecraft could fly through the plumes, collect samples, and analyze them for biomarkers, molecules that would indicate the presence of living organisms. NASA and other space agencies are actively studying concepts for such a mission. Iapetus is another strange moon. It's about 1,500 kilometers in diameter, large enough to be spherical, but it has one of the most bizarre appearances of any object in the solar system. One hemisphere of Iapetus is bright white, made of relatively clean water ice. The other hemisphere is dark brown, almost black, covered in a mysterious material that absorbs almost all sunlight. The contrast between these two hemispheres is stark, making Iapetus look like a gigantic yin-yang symbol. Cassini's observations suggest that the dark material is carbon-rich organic compounds, possibly brought in by impacts from comets or created by photochemistry in Iapetus's distant past. Iapetus also has an enormous ridge that runs along much of its equator, a mountain chain that rises 20 kilometers above the surrounding surface. This ridge is unique in the solar system, and its origin is still debated. One theory is that it's the collapsed remnant of a ring system that Iapetus had in its early history. Material from the ring gradually fell onto the moon's surface, piling up along the equator and creating the ridge. Another theory is that the ridge formed when Iapetus was spinning much faster than it is today, and the centrifugal force caused the equator to bulge outward. When Iapetus's rotation slowed down, the bulge solidified, leaving the ridge behind. Mimas is a small moon that looks remarkably like the Death Star from Star Wars, thanks to a massive impact crater called Herschel that covers much of one hemisphere. This crater is about 130 kilometers across, almost a third of Mimas's diameter, and it was created by an impact that nearly shattered the moon. If the impactor had been slightly larger or struck slightly harder, Mimas would have been destroyed, adding its debris to Saturn's ring system. Instead, Mimas survived, and the crater remains as a reminder of the violent collisions that shaped the Saturn system. Hyperion is an irregularly shaped moon that tumbles chaotically as it orbits Saturn. Most moons rotate in a predictable way, with one side always facing the planet, locked by tidal forces into synchronous rotation. But Hyperion's rotation is chaotic, meaning its orientation changes unpredictably over time. This chaos is caused by Hyperion's irregular shape and its gravitational interactions with Titan, the largest moon. Hyperion's surface is also bizarre, covered in deep craters and a sponge-like texture, unlike any other object we've observed. The spongy appearance might be due to the moon's low density and weak gravity, which allows impacts to excavate deep, sharp-edged craters without causing much compaction of the surrounding material. Many of Saturn's smaller moons play important roles in sculpting and maintaining the rings. Prometheus and Pandora, two small moons orbiting just inside and outside the narrow F-ring, are called shepherd moons because their gravity keeps the ring particles confined to a narrow band. As Prometheus orbits inside the ring, its gravity pulls on the nearest ring particles, slowing them down and causing them to move slightly outward. As Pandora orbits outside the ring, its gravity pulls on the outer edge, speeding up particles and causing them to move slightly inward. The net effect is that the ring particles stay confined between the two moons, creating the narrow, braided structure of the F-ring. Other small moons orbit within, gaps in the rings themselves. Pan orbits in the Encke gap in the A-ring, and its gravity clears out this gap, sweeping up any particles that drift into its path. Daphnis orbits in the Keeler gap, also in the A-ring, and creates beautiful wave patterns in the ring edges as it passes by. These moons are tiny, just tens of kilometers across, but their gravitational influence on the rings is surprisingly large. They're like cosmic gardeners, constantly tending the rings and maintaining their structure. Some of Saturn's moons share the same orbit, a configuration that's almost unheard of elsewhere in the solar system. Janus and Epimetheus orbit at almost exactly the same distance from Saturn, separated by only about 50 kilometers. This is far closer than two moons should be able to orbit without colliding or gravitationally, disrupting each other. But Janus and Epimetheus have a special arrangement. Every 4 years, as the inner moon catches up to the outer moon in its faster orbit, the two moons exchange orbital energy through their mutual gravitational attraction. The inner moon gets boosted to a higher, slower orbit, and the outer moon drops to a lower, faster orbit. They effectively swap places, and then they continue on their separate ways for another 4 years until the next exchange. It's a gravitational dance that's perfectly choreographed by orbital mechanics, and it's been going on for millions of years. These moons interact with Saturn and with each other in complex ways. Their gravity shapes the rings, creating gaps and divisions and spiral waves. They exchange material, with ice from the rings falling onto moons and material from moons being blasted into space by impacts. Some moons are embedded in faint, dusty rings created by meteoroid impacts on their surfaces. Every collision that occurs on one of these moons ejects a spray of dust particles into orbit, and these particles gradually spread out to form a ring. The G-ring, for example, is probably created by impacts on small moons or moonlets orbiting within it. The Saturn system is like a miniature solar system, with the planet at the center and a family of diverse moons orbiting around it. Each moon has its own personality and mysteries. Some are geologically active, driven by tidal heating. Others are ancient and cratered, preserving a record of the early solar system. Some have atmospheres, subsurface oceans, or organic chemistry. Others are just bare rocks or balls of ice. Together, they form a complex, interconnected system where every object influences every other object through gravity, collisions, and the exchange of material. Understanding this system helps us understand not just Saturn, but the processes that shape all planetary systems, including our own. These moons interact with Saturn and with each other in complex ways. Their gravity shapes the rings, creating gaps and divisions and spiral waves. They exchange material, with ice from the rings falling onto moons and material from moons being blasted into space by impacts. Some moons even share orbits, orbiting at the same distance from Saturn but separated by 60 degrees, locked in a gravitational dance called a Lagrange point. The Saturn system is a miniature solar system with the planet at the center and a family of moons orbiting around it, each with its own personality and mysteries. In many ways, studying Saturn is like studying the solar system in miniature. The same processes that shape the formation and evolution of the planets also shape Saturn and its moons. Accretion, migration, collisions, tidal forces, all of these played a role. By understanding Saturn, we learn about the solar system as a whole, and by extension, about other planetary systems around other stars. Many exoplanets discovered so far are gas giants similar to Saturn and Jupiter, and some of them are even more extreme, with orbits that take them incredibly close to their parent stars or that are highly elliptical. Understanding how Saturn formed and evolved helps us understand how those distant worlds might have formed and what they might be like. But there's also something deeply personal about Saturn. It's not just a scientific puzzle, it's a source of wonder and inspiration. When you look at Saturn through a telescope, even a small one, and see those rings with your own eyes, it's a moment that stays with you. The rings are so delicate, so improbable, and yet so real. They're right there, floating in the darkness of space, a reminder that the universe is capable of creating beauty on a scale that's almost incomprehensible. Saturn has inspired countless artists, writers, and dreamers. It's appeared in science fiction stories, in paintings, in music, and in poetry. It's become a symbol of the cosmos, a representation of the mystery and majesty of the universe. And that's fitting, because Saturn really is something special. It's a planet that shouldn't exist, a planet that defies the rules, and yet there it is, shining in the night sky, waiting for us to uncover its secrets. So when you think about Saturn, don't just think about the science, although the science is fascinating. Think about what Saturn represents. It represents the idea that the universe is full of wonders, full of things that surprise us and challenge us and make us question what we think we know. It represents the idea that even in a cosmos governed by laws of physics, there's room for beauty and complexity and mystery. And it represents the idea that we, as humans, have the ability to look up at the sky, to ask questions, and to seek answers. Saturn is a reminder that exploration is never finished. There's always more to learn, always more to discover. The Cassini mission ended when the spacecraft plunged into Saturn's atmosphere, burning up like a meteor to avoid contaminating any of Saturn's potentially habitable moons. But the questions Cassini raised are still with us. How exactly did the rings form? What's happening deep inside Saturn's core? How do Saturn's moons interact with the planet and with each other? What secrets are hidden in Titan's methane lakes or Enceladus's subsurface ocean? These questions will drive future missions, future discoveries, and future generations of scientists and explorers. In the end, Saturn's existence is not a paradox. It's a testament to the richness and complexity of the universe. The fact that Saturn is so strange, so unexpected, so full of surprises, that's not a bug. It's a feature. It's what makes the universe interesting. If every planet formed in a predictable way and behaved exactly as we expected, the universe would be a boring place. But it's not. The universe is wild and chaotic and full of planets like Saturn, planets that break the rules and force us to think harder and look deeper. So the next time you hear someone say that Saturn shouldn't exist, remember that they're right. By all accounts, Saturn is impossible. It's too light, too warm, too beautiful, but it exists anyway, spinning through space with its rings gleaming in the sunlight, a cosmic contradiction that refuses to be ignored. And in that impossibility, in that refusal to fit neatly into our theories, Saturn teaches us the most important lesson of all. The universe doesn't care what we think should be possible. It does what it does, and it's up to us to keep up. Saturn is a gift, a window into the violent, chaotic history of the solar system, and a reminder that even after billions of years, the cosmos can still surprise us. It's a planet that challenges us to think bigger, to question our assumptions, and to never stop exploring. Because if a planet as impossible as Saturn can exist, if rings as beautiful and improbable as Saturn's rings can form and persist, then what else is out there waiting for us to discover? What other wonders are hiding in the darkness of space, waiting for us to turn our telescopes in the right direction and ask the right questions? Saturn shouldn't exist, but it does, and that makes all the difference. That's the paradox, the mystery, and the beauty of this ring giant floating in the outer solar system. It's a planet that defies explanation, and in doing so, it invites us to keep looking, keep learning, and keep wondering, because the universe is full of impossibilities, and Saturn is proof that sometimes the impossible is exactly what we need to inspire us to reach further and dream bigger. As we drift off into the quiet contemplation that Saturn inspires, we can imagine ourselves floating near those rings, watching the ice particles shimmer in the distant sunlight, feeling the slow rotation of the planet beneath us, and knowing that we're witnessing something that shouldn't be, but is. The gentle hiss of Saturn's storms, the whisper of its winds, the soft glow of its auroras, all of it becomes a cosmic lullaby, a reminder that the universe is vast and beautiful and full of mysteries that we're only beginning to understand. Saturn's impossibility is its gift to us. It reminds us that the cosmos is not a machine, predictable and sterile. It's a living, breathing tapestry of matter and energy, constantly creating, constantly destroying, constantly surprising us with phenomena that challenge our understanding. And in that challenge, we find inspiration. We find the drive to explore, to question, to learn. We find the courage to look at something that shouldn't exist and ask, how did this happen? And in asking that question, we take another step toward understanding our place in the universe. So let Saturn stand as a monument to the impossible, a reminder that the universe is far stranger and more wonderful than we can ever imagine. Let its rings shine as a beacon, calling us to explore further, to dig deeper, to never accept that we've learned everything there is to know. Because every time we think we've figured out how the universe works, along comes something like Saturn, a planet that breaks the rules and forces us to start over, to rethink our theories, to embrace the unknown. And as you close your eyes tonight, let the image of Saturn drift through your mind. Picture those rings, delicate and vast, stretching across the darkness of space. Picture the storms swirling in the planet's atmosphere, the lightning flashing in the clouds, the ice particles colliding and bouncing in the rings. Picture the slow, majestic rotation of the planet, the gentle dance of its many moons, the ancient scars of migration and chaos written into its very structure. Let Saturn become a part of your dreams, a symbol of the beauty and mystery that fills the cosmos. Because Saturn shouldn't exist, but it does, and in that simple fact we find everything we need: wonder, mystery, inspiration, the reminder that the universe is full of impossibilities and that sometimes those impossibilities are the most beautiful things of all. So rest easy, knowing that somewhere out there Saturn is spinning through the darkness, its rings gleaming, its mysteries waiting, and its impossibility standing as proof that the universe will never stop surprising us. Thank you for joining me on this journey through the paradox of Saturn. If you enjoyed exploring the mysteries of the ringed giant, I'd love to hear your thoughts in the comments below. What aspect of Saturn fascinates you most? The impossible rings, the liquid metallic hydrogen core, the violent history of planetary migration? Drop a comment and let's continue the conversation. And if you're curious about more cosmic mysteries and want to drift off to sleep with the wonders of the universe in your mind, consider subscribing. There are countless more impossibilities waiting to be explored. From the edges of black holes to the birth of stars, and I'll be here to guide you through them all. Until next time, keep looking up, keep wondering, and remember that the universe is far stranger than we can imagine. Sweet dreams and clear skies.